Okay, so hi there. So in this video, I want to show you how to approach and solve problems that involve materials with different indexes of refraction. And this will give us a chance to both see how to use the Snell's law that we talked about in the previous video, and also kind of how to approach problems that involve a bit more geometry than we've had in a lot of recent cases. So the problem's written like this. A flashlight is held at the edge of a swimming pool at a height of 1.5 meters such that its beam makes an angle of 41 degrees with respect to the water's surface. The pool is 2.75 meters deep, and the index of refraction for air and water are 1 and 1.33 respectively. We're asked, what is the horizontal distance d from the edge of the pool to the point at the bottom of the pool where the light strikes? Write your answer in meters. So at first we could try and approach this with our standard thing. We're interested in getting the parameter d, which is written here. And so I'm not going to repeat it because we're going to need a lot of space for this particular problem. So we're looking for this parameter d. What we know is the height the flashlight is above the surface of the pool. We know the distance, 2.75 meters, is the depth of the pool. And we know the angle that it strikes the surface at is 41 degrees. So these numbers are three of the parameters were put in there. We also have a couple other things, which are the indexes of refraction of air and water, which I'll also write down here just to make sure we have them. So we have N1 equals 1 and N2 equals 1.33. So as far as that goes, we could write down what we need, but at this point we have a slight problem in that whereas in previous problems we've been able to look for algebraic relationships between what we want and what we have, in this case we can't just do that. There's no single equation that I've talked about that gives you those sorts of things. They are related to each other, but to see those relationships, we need to sketch the system. And so I am going to try to make a decent drawing of this system. So first of all, we know we have a swimming pool, so let's draw that. Here's a swimming pool. Okay. And we also know that we're holding a flashlight above the edge of that swimming pool. So there's a flashlight right around, say, let's say about here. It's an ugly flashlight, but it'll work. So we also know that this distance is the thing is h. And we know this distance from the pool to the bottom is d. Great. So, and what we want to know is how far beneath the pool does the light strike it? But we have to sketch that properly. So we know that the light from the flashlight comes down. Actually, let's do a little bit of adjustment here. So we need to be a little careful about our definitions here. The height we are interested in is from the flashlight. So it goes from the surface up to there. That's h. So to be clear, this is the height h. From there to there. Okay, Now, the beam of the flashlight starts from height h and goes down to the surface somewhere. And it hits the surface and makes an angle of 41 degrees. Now, for the purpose of drawing, you don't have to be super precise about that, but being reasonably precise is good. So let's make that where it ends up. Okay. And then it's this angle here that is the angle theta. This is what theta is, because we're explicitly told it makes an angle of theta degrees with respect to the water surface. So this is 41. Now that's where it hits the surface, but that's not all we need. We also need the thing to go to the water. And we know because water has a different index of refraction, it won't follow exactly the same path. It'll be, and since we're going from something with low index to high index, it'll come down at a slightly steeper angle. Okay, so we got that. What we're interested in this case, is this distance. This is the thing we want. And that is the distance we're going to be calling big D. Okay, so we got that. So this is what we want. This is what we know. We also know the index of refraction of the two materials. But now we can see this problem's a little more complicated than you might have thought, because the light isn't just following a single trajectory. This isn't like a straight line. So D is actually made up of two parts. We can first say, for example, what's the distance light took till it got to the surface? We can give that a name, since no one has asked us what to call it. We can call that distance D1. And then we have the distance from that the thing took in the water. That we can call, for example, D2. Okay. So, and what we know is, so the thing is, D can be written as the sum of two things, as the sum of those two distances. It's often easy, and so this gives us a sense that this one's going to be complicated. We have to calculate two distances to make this work. And this is part of the reason I have an Excel spreadsheet open, because we've got to calculate a few things. We can't do this all in this space very efficiently. Okay, so we need to figure out what D1 is. And D1, just to be clear, is this distance from the flashlight end to where it strikes the surface. Now, if you notice this, we have a right triangle. This is a right angle. It's got a height h at a base that is D1. And it has this angle is theta. So this is a right triangle. You could figure, we know this one we can figure out fairly easily. D1 is something we can get from h and theta. Now, we have a right triangle. We are considering this angle. So we have what we have is one of the sides, and we want the other side. So the relevant trigonometric relationship is the tangent rule. So that says h over D1 equals tan the tangent of theta. So again, tangent of theta is the ratio of the opposite over the adjacent. So this relationship is the one we can use to figure out what D1 is. Now, notice this works. We know H, we know theta, we want D1, so we got everything we need. So all we have to do is solve this for D1. So first thing we do, we multiply through, and we multiply both sides by D1, we get H equals tan theta times D1, and then you divide by tan theta, and you get the expression D1 equals H over tan theta. Okay, and these are both parameters we know, so we can actually do that calculation. So to see that, let's just do that. So we can say H is 1.5. Theta is equal to 41 degrees times 3.14 divided by 180, because whenever you use a tangent function in Excel, it will do it in radians. So just to verify that, so if we do equals tangent of this, notice we get a thing about 1, which makes sense for something right around 45 degrees. So this is tan theta. Okay. So now all we have to do is take this, multiply it by this, and what we get? We get about 1.3. Oops. I multiplied. That was wrong. Take this and divide it by that. Then we get a number of about, say, 1.73. So now we have a new thing we know. We now know D1 is about 1.73 meters. Okay, great. We got that. Now, notice it also makes sense. This thing is, so if this was a 45-degree triangle, D1 and H would be the same. In my case, theta is less than 45 degrees. So this is a relatively grazing angle. Okay. If this is a more grazing angle, you expect this distance to be a little longer than this. And that's in fact the case, but not very much. So that works. So we've got D1. Yay. Now, I'm just going to erase this and start to work on what D2 is. Now we have to figure out what D2 is. Well, we know what D is, and so we have another one of these slightly, shall we say, so we know what this distance is, it's D. We know what this length is. This length here is D2. And this is another right triangle. So we can figure out what D2 is in terms of D if we knew this angle, which I'm going to call theta W because it's in the water. Call it theta pool if you want to. So we have another right triangle here. And we can use the law of tangents again because we're given the two sides of the two legs of the triangle instead of the hypotenuse. So we can say D2 over d is tan theta w. And that is true. So you can even solve this pretty quickly for d2. You could just say multiply out by the little d, and you get d2 is d times the tangent of this angle theta w. Great. And we know d is 2.75 meters. So we can do that. That's easy. We do d equals 2.75, d, which is 2.75. Great. Now, wait, we need just theta w. Wait, do we know that? Well, if we look at it, it's the angle of refraction. We can figure that out because we know this angle. Now, this is again a case where you want to be careful because there is a relationship that connects the thing we need. So now, remember, what we really want is d, which means we need d1 and d2. We've got d1. We're now trying to get d2, which requires us to get theta w. But we need to now express theta w in terms of other things. So how are we going to do that? Well, we're going to use the law of refraction, which I'm writing over here. N1 sine theta 1 equals N2 sine theta 2. But if you think about it, theta 2 is literally the thing I've just called theta w. So realize what we've got here. Sine theta w, so that's the thing we want. N2 and N1, we're given those, 1 and 1.33, and sine theta 1. Now, here's where you do have to be careful. There's a quick tendency for people to go, oh, I know what theta is. It's 41 degrees. I was given that. I'll just stick that in there. That won't work because theta is this angle. That's not the angle we want. For the law of refraction, we need this angle. This is theta 1, not this one. And this is where often these problems can get a little tricky. But we can notice that theta plus theta 1 is 90 degrees. So theta 1 has to be, just remove theta on both sides, 90 degrees minus theta. And we know what theta is. It's 41 degrees, so it's 90 minus 41. That's something I can do relatively easily. 90 degrees minus 41 degrees is 49 degrees. Okay, so I do know this. This is 49. I know this and this, so I can figure out what sine of theta w is. Sine of theta w, just divide out by n2, is going to be n1 over n2 times sine of theta 1. And we can evaluate all of that. we'll do that down here. So now we just note, so theta 1 is 49 degrees. Sine of theta 1 is going to be sine of this thing times 3.14 over 180. Again, we have to convert to radians or else this doesn't work on Excel. Okay, that's 0.75. Now we can say, now we can also get n1 over n2, which is the other thing we need. That's 1 over equals 1 over 1.33. And then we get sine theta w, which is just this times this. So sine of theta w is 0.567. We can then figure out what theta w is just taking the arc sine of that, which gives me a number that is again in radians. So I need to take this and multiply it by 180 over 5 to get it in degrees, and turns out to be about, 34 degrees. So less than this angle, maybe drew it a little steeper than I should have, but it's fine. So D is that. So now we have what we need. We know theta W is 34.5 times, so change it back into radians. Obviously, you don't have to do this, but I'm going to. And then we're going to say tan of theta W is equal to the tangent of this. Cool. And then we're going to say D2, just like this is D1, is this equals this times this. Seems a little high. Oh, we'll try it out. So here we get now, so we get an expression that D2 is need 9 meters. And now we've got the two D's we need. We can add them together. We can do that anywhere we want. We can do that here. And just say D is just this plus this. And we get something that's around. So if we did that right, it should be about 3.6 meters. So let's see if this works. And submit. It worked. Yay. So this, in fact, was the correct distance. Now, notice D1 and D2 are almost the same, and I didn't draw them that way here. That's because I didn't know exactly how much everything was going to bend. But despite that, this sketch was helpful for figuring out how to approach and solve this problem. And it shows how being careful about your angles is important in these situations. Anyway, thank you for your time and attention.